cold and dry and a place that's bombarded by cosmic rays, really a place that's inhospitable to hosting life today. What we've learned over the last couple of decades in our exploration of Mars is that Mars was much warmer and wetter a few billion years ago, and that some of the environments on Mars actually could have had all of the right ingredients to support microbial life at about the same time that life emerged on Earth. If I could have the first graphic, there it is. You can see on the far left, we began our rover program in 1997 with Sojourner, and all of these rovers have helped pave the way for our understanding of the Mars environment and what Mars is like and how it has evolved over time, and led us to the Perseverance mission that we're waiting to land on Thursday. So the Sojourner rover kicked it off in 97, followed by Spirit and Opportunity, shown there towards the left. Spirit and Opportunity were really following the water on Mars, trying to identify, was liquid water ever present in substantial quantities over an extended period of time on Mars? And they found rocks that really did require water to be present in order for them to be formed. The next step, of course, was the Curiosity rover, and Curiosity went to Gale Crater, looking to identify, searching for habitable environments, exploring habitability on Mars. And in Gale Crater was able to confirm that yes, liquid water was present on Mars for an extended period of time, long enough to deposit sediments on the floor of Gale Crater, to generate and create clays that are found in some of the units there at Gale Crater. And also we found complex organic molecules. So with the water and the complex organic molecules, two of the real key ingredients to life were present, and in a habitable environment there that life could have possibly started to take form. And all of that led the way and prepared us to design the Perseverance rover, which is really now our first mission, our first mobile astrobiologist that's out really seeking the signs of life. Perseverance is our next step in exploration, and we've learned from everything that we've learned, we were able to better identify exactly what kind of site we wanted to visit that had the highest probability of having preserved ancient microbial life, and Ken Williford's going to speak a little bit more to that in a few minutes. We also are now better prepared to design the instruments and the experiments that we want to conduct on the surface of Mars, specifically designed to look for those markers, those biologic markers that can give us a hint that perhaps there was life early in Mars's history and that it might be preserved in those rocks at Jezero Crater. And then, of course, the next step beyond Perseverance will be the ability to bring samples back. So Perseverance is going to identify rocks that we'd like to bring back to Earth, drill the rocks in soil, save them on the surface for that next mission that you see, which is Mars Sample Return, which will launch those samples back to Earth, back into orbit, and then captured and returned back to Earth eventually, and then preparing the way for human exploration at some time in the not too distant future. The Mars Sample Return project, of course, is probably the most challenging thing we've ever attempted within NASA, and we don't do any of these things alone. Between our partnerships on Perseverance and partnerships for Mars Sample Return, we have almost a dozen international partners that we work with, and together we are hoping to learn if life ever existed in the ancient past on Mars. And so with that, I'd like to hand it over to Ken, who's going to talk a little bit about what we might find in Jezero Crater.
Well, thanks, Lori, for that great introduction. And I want to start out by just sharing with you all how fortunate I feel, how excited I am to be, just days away from really a momentous occasion. Technically, with all the work it's taken to get our spacecraft to where it is now and in the state that it's in now, and then also scientifically. Just for me personally, the opportunity to be a part of this mission, which is directly looking for life on other planets, it's really a scientific dream come true. It's not an exaggeration. So it's going to be a big week for us. And pulling back a bit, if you take a minute to think about it, the implications of the science of this mission are really enormous. I mean, we're Mars 2020 and Mars Sample Return, as Lori described, are about really an age-old question. Are we alone in the universe? We say that a lot, but about these astrobiology missions, but it's a big question if you stop to think about it. We know that life exists on Earth. We know Earth is a very hospitable planet and has been for billions of years. Life obviously thrives here today. Um, but are we alone in a sort of vast cosmic desert, just flying through space, or is life much more common? Does it just emerge whenever and wherever the conditions are right? Big basic questions, and we don't know the answers yet. So we're really on the verge of being able to potentially answer these enormous questions. Um, to start to get a feeling for the kinds of things we might uh, hope to find at our landing site in Jezero Crater, a group of us from NASA, some NASA scientists and some ESA scientists, European Space Agency scientists, went to Australia to a place called the Pilbara. So if we could just get the video. And this place in Western Australia um, holds what is really the best early evidence for life on Earth. So this is the rocks that were deposited about 3.5 billion years ago here on Earth, where pretty much any scientist who works in this field can agree we have very good evidence for life there. And what does that look like? And so here you see us actually exploring, the shores. Actually, not in this specific spot, but we did on that trip explore the shores of an ancient lake. And I'll just hold up this rock sample that I brought back. Hopefully you get a good focused image of that. You can see it on your screen as well in a picture. But this is a stromatolite sample that I brought back from a 2.7 billion year old lake deposit. So it originally would have been oriented like this with a dome of microbial mats. And so these are structures that form when little microscopic single-celled organisms like bacteria join together in communities and layer one on top of the other, and sometimes exude these sticky substances that can trap and bind sediment particles there. The organisms themselves can also stimulate the precipitation of minerals, thereby entombing themselves, sort of making their own microbial fossil, which, as we can see in the case of that rock I showed you, can be preserved for billions of years. And so, in a sense, to answer these big questions, we're going back in time 3 to 4 billion years ago to look at this very ancient lake system and look at all the different sub-environments in and around that ancient lake, and asking, what was this environment like? Could it have supported life? But then taking that next step, as Laurie said, and looking for any evidence that life may have left behind, like these stromatolites, or what we might more likely expect, something significantly more ambiguous. So that ambiguity that tends to be a part of the search for the most ancient record of life on Earth, and we can expect it to be the same on Mars. That ambiguity is why we need this incredibly complex and capable scientific payload. So to start telling you a bit more about that, I'll pass it to Luther Beagle, who's the principal investigator of the Sherlock instrument on Mars 2020.
Hey, Ken, thanks for that great introduction. I really appreciate it. When I got to JPL in April of 1997, we were getting ready to land Sojourner rover on Mars, and it was a very exciting time to be here, and I thought stuff like that happened all the time. Didn't realize exactly how much hard work went into it until later on when MER and then MSL and now 2020 lands. But it's a great time to be here, and I'm honored to be part of this project. The science we're going to do is spectacular. As Ken mentioned, I'm the principal investigator of the Sherlock instrument. That's an arm-mounted instrument on the end of on the Perseverance rover. We chose Sherlock because we're going to Mars to look for clues. We're looking for clues for two specific things. One, we want to know whether Mars could have been habitable in the past. That is, were the conditions right to have organic material turn into microorganisms and with the origin of life. The second thing we're looking for is evidence of that origin of life. We're looking for clues with two different things. And this is a picture of the instrument that you're seeing here now. We have two different cameras on this instrument. The camera on the right is we call Watson, which is like a magnifying glass. Sherlock always has magnifying glass with him. And what Watson does is Watson takes microscopic images, and it also takes panoramic images as well. So you can take a picture of the rover You've seen the rover selfies. That was done with Molly on MSL. This is a reflight of that camera. And we were able to take pictures of the rover, and we're also able to take pictures of the rock. And we can actually zoom in on the rock and get down to really fine spatial scales. The second camera is the spectrometer part of the camera. We take even finer images with that particular camera, and we do spectroscopy. We do two different types of spectroscopy. Raman spectroscopy, which tells us what kind of molecules are present on the surface, which gives us organic material, chemicals, and mineralogy, and fluorescence spectroscopy, which identifies organic materials. So how we work on the end of the arm is this is a movie you're about to see, and it shows how Sherlock actually is moved on the robotic arm. This robotic arm, you can see Sherlock on the outer part of the arm here. We're attached to the drill. Pixel, our sister element, our sister instrument is on the other side of the rover, and Pixel does elemental abundances the same way we do on the microscopic scale. We're looking really at really fine scales on Mars on the order of 100 microns. That's about the size of a human hair, and we're looking for clues in those very small regions. This is the way the arm moves. This is a video showing how we get deployed. We don't bring the sample to us. We go to the sample. So you can see really how slow the arm moves and how deliberate it is. The arm is really, really big, and we can actually, we command it to about 5 centimeters above the surface. We're a contactless instrument. And what we are actually doing is, slide one, is we're able to map things out. We're able to take an image of a very fine microscopic image, and we're able to take our laser and raster it across the surface and identify organic material, minerals, and the like. And we're able to do that with Pixel too. So the image on the left is a stromatolite like Ken showed that we obtained from Australia, and we took two different images at the bottom. The Sherlock one is in the small red box, and the Pixel one is in the larger red rectangle box. Pixel identifies where different elements are, and we map them out, and so we can map out context in the images with actual organic and mineral maps on the right. And this tells us a lot more about the rock than just doing one instrument by itself. So we can take our measurements and combine them with Pixel and then combine them with SuperCam, which we'll hear about in a second, and get a really better idea of what the entire sample is all about. The next slide shows a stromatolite. And this particular stromatolite is from the Pilbara region, and we got it a few years ago, and we wanted to show what we could do with Sherlock. And so what we did was we scanned across the surface. We took an image, that's the top image, and we scanned across the entire image, and wherever you see deep blue is where there was a microorganism, a single-celled organism existed, and where you don't see any dark blue, you see that's not, there's no little or no organisms there. So we scan across, and where you see organic, or excuse me, when you see microorganisms on the outside of the rock, you can see them in cracks, you can see them in fissures, which is where you would think that organisms would live because they have accessibility to both water and nutrients. There were two features on this particular scan that we weren't quite sure about. One is in the upper right-hand corner, the dark blue on the rock, and then one is on the bottom left-hand corner, the purplish feature down there. What these two features are actually the fingerprints of a postdoc that accidentally picked up the rock. So this shows you exactly how sensitive Sherlock is. We actually were able to identify the fact that he picked up this rock without any gloves on, which then contaminated the surface, and we could get his fingerprints from that surface. So that's kind of what Sherlock does. And for the to understand where our samples are looking at in context, I'm going to throw it over to Jim Bell, who's the principal investigator of Mastcam-Z. Jim?
Hey, thanks, Luther. I am super excited about being able to talk about the science of our mission, and I'm also just super fortunate to have been able to participate in all 4 of NASA's rover missions to Mars so far in my career. And so this upcoming 7 Minutes of Terror on Thursday will be my 5th ride down these particular Class 5 rapids, and just really looking forward to the great ride the engineers are going to give us, and then the great science that we're going to do with this mission. I'm here in the Mission Operations Center at Arizona State University in Tempe. This is the Mission Operations Center for the Mastcam-Z camera-mounted instruments on Perseverance. This is where our part of the science and engineering team will be watching the landing. Because of COVID, the 400 or 500 members of the science team can't be all together at JPL like we normally are and jumping up and down, yelling and screaming with the engineers. We can't do that. So we're all back at our home institutions, and we'll be running our part of the investigation here from campus in Tempe. So we'll be doing the day-to-day health assessment of the cameras, the calibration, the image processing, and getting that information out to the rest of the science team, as well as to the public via the JPL and NASA public websites. So if I could have my first slide up. So this rover is loaded with engineering and science cameras galore and microphones, and you'll hear more about those later. This rover and this mission is going to be a feast for the eyes and ears. It's really going to be spectacular. 23 cameras on the rover and its descent stage itself, plus 2 more cameras on the helicopter, 25 cameras total, the most camera-heavy mission of deep space robotic exploration ever sent out there. So very, very excited about that. And the cameras that we'll be operating and using to help achieve our mission goals are called Mastcam Z. If you go to the next one, please, next slide. You can see them up on the mast, and the technician here doing some final cleaning and checkout. Those square aperture ends there, you can see, and I've got a little model here I can show off. It's about the size, each one of those is about the size of a typical can of tennis balls, for example, and we have 2 of them. The 2 of them give us stereo vision. They're the Z in Mastcam Z stands for zoom. So we can go from wide angle stereo view of the landscape all the way to telephoto, super close up, high resolution view of the landscape. We can resolve features on the millimeter scale close in to the rover, and on the centimeter scale off at the distance. We can see, for example, something and resolve something the size of a housefly at the length of a football field. So here's an example of the zoom capability in the next slides here, taking the cameras and pointing them out the laboratory window. We go from the wide angle view of that ridge, it's about 1 kilometer away, all the way zooming in to full telephoto. So we've spent the past 7 years designing, manufacturing, testing these cameras in close collaboration with our colleagues at Mail and Space Science Systems in San Diego, who have done a lot of really great deep space cameras. We took the engineering model cameras out in the Mars yard just last week. This is the engineering model rover. We used this to test everything that we're going to do on the real rover. And we took this beautiful 360-degree panorama at a relatively wide angle setting. So about 142 images go into this RGB color panorama. And so we can see all the way around and the rover itself. And this is an example of one of the early products that we'll get from one of the early sols on the mission. After we pop that mast up and take our first 360-degree look around. We can also project that into a selfie. Here's the same view projected looking down onto the rover. Of course, the cameras tilt up and down as well. We can look down on the rover and take a picture of the deck for characterizing the things on the deck that the engineers are interested in, as well as our calibration targets, which we're very interested in to make sure we get the colors right. So these are just some examples of the kinds of things that we won't be seeing the Mars yard in JPL. We'll be seeing Jezero's backyard on Mars starting next week. So we're super excited about that, and really excited especially about sharing all of these images with the public as they start coming down. Okay, so you saw a bunch of stuff going on that mast, up on top of that mast, including the Mastcam Z as well. We share that space with navigation cameras and with another science instrument called SuperCam, and you're going to hear more about that. I'll turn it over to Sylvestre Maurice for more details. Take it away.
Yeah, thanks so much, Jim. Thanks, really great. I'm Sylvestre Maurice. I'm the Deputy PI of SuperCam, and I'm glad to attend this briefing from Toulouse and my home institution here in France. Very lucky to be here. SuperCam is largely inherited from ChemCam, a very active instrument on Curiosity that has shot its laser more than 800,000 times so far. Similarly to ChemCam, SuperCam has been built by the Los Alamos National Lab in New Mexico and France. But if SuperCam seems just like ChemCam, it is actually very different. Let's look at the video now. SuperCam is made of 3 parts. The mast unit is at the top of the mast. It's as high as 2 meters, and it looks like the Perseverance high. In a rover body, you have the body unit that handles communication with the rover. And at the rear, we have calibration targets to obtain reference measurements on well-known standards. SuperCam consists of 3 spectroscopy techniques. Just like ChemCam, the mass unit fires an infrared laser, creates a plasma, and within the body unit, the return line is being analyzed. And thus we find the atomic composition of the targets, how much iron, titanium, sodium, and so on. We also have 2 new techniques. Raman spectroscopy, it's a green laser to vibrate the molecule, just like Sherlock, with a different kind of laser. We're also analyzing infrared light from the sun as it's being reflected by the rocks. These are very new. Both techniques yield molecular structure and possibly organic molecules. To find out where we're shooting at, we have also a microscopic imager. It's another camera on Jim's list. High resolution, very small field of view for ourselves. And at last, but not least, we have a microphone, one of the 2 microphones on a rover, to listen at the wind, listen at the rover, and also the infrared laser shooting at Mars. Well, you can see that SuperCam is quite a complex instrument, and yet a very powerful one. It can look at the atmosphere, at rocks, from 2 meter distance to up to 7 meters without moving the rover, and at scale as small as 1 millimeter. So SuperCam will characterize in situ the habitability and search for traces of life.
List presenters, we are now ready to take media questions. Remember to press *1 to get put in the queue, and please direct your questions to one of the panelists in particular. We're also taking questions through the hashtag Countdown to Mars. Our first caller is Chelsea Goad with Space.com. Good afternoon, Chelsea.
Good afternoon. Thank you for taking my question. My question is for Ken Williford. You mentioned that you and the larger team studied stromatolites in Australia to demonstrate finding and scanning microorganisms in rock cracks and fissures. Do you expect that if and when Perseverance does identify evidence of ancient organisms on Mars, that these organisms might be similar to the microbes you studied as an analog in Australia?
Wow, it's a fantastic question. So we did go to this specific location in the Pilbara in Western Australia for an important reason, and that's because in a certain way, looking at the earliest evidence for life on Earth is our best analog to the challenge we have in front of us. So the similarities are many. The environment we were looking at in Australia, in the case of at least this sample that I showed you, was an ancient lake. We looked at ancient lake environments there. And I think it's fair enough to say, of course I could go on forever on this topic, but it's fair enough to say that life that we're looking for, sort of a life as we know it, would be cellular, that prior to, we know from the record of life on Earth, that complex organisms, complex multicellular organisms like we're familiar with today, animals and plants, didn't evolve until fairly late in the history of the Earth after oxygen rose in the atmosphere to appreciable levels. So we don't think anything like that happened on Mars, and so we think it's as likely as not that anything that was alive on Mars 3.5 billion years ago would be similar to Earth bacteria and similar organisms called archaea, which are the kind of organisms that we think made these stromatolites that we find in Western Australia.
Thank you, Ken. Our next caller is Deanne Divis from Al Jazeera. Good afternoon, Deanne.
Good afternoon. Thank you for this opportunity. This one is to Ms. Glaze. It was mentioned in the last briefing that NASA hopes to use activities on the lunar surface to inform future Mars exploration. I was wondering if that might also be true from the Mars work that your team is doing. Will it inform the work that will be happening through Artemis or any other lunar activities?
It's a really interesting question, and I think everything that we do is helping to inform everything across the board. We're working together, always science and exploration working hand in hand, science enabling exploration, exploration enabling science. And certainly I think some of the things that we're going to be doing on Mars, thinking about how to take advantage of resources that are local. Of course, they would be a little differently when we're talking about the moon, but thinking about how we do this actually in situ are things that will feed forward. So there's a lot we can do there working together. I don't know that I have anything specifically as far as a direct link, but as I said, we work together really closely.
If I might ask a follow-up, Rimfax, could you speak to Rimfax and what you'll be looking for with Rimfax?
I can speak a little bit to Rimfax, you bet. So Rimfax is a really interesting instrument that is actually a ground-penetrating radar that's going to be able to see several feet, tens of feet below the surface, and that allows us to actually better understand what the structure is beneath the surface that we can see and that we're going to be driving over. So like I said, we know that there should be these sediments that will be present at the bottom, beneath the rover, but somewhere beneath that might be able to see if there's any other geologic structure within those sediments or maybe even the base of those. So using Rimfax, we'll be able to better understand the full three-dimensional scope of what the geology looks like in Jezero.
Thank you.
Thank you so much, Lori. Our third caller is Leo Enright from Irish Television.
Thanks very much, Marina. I was wondering, your mission is clearly to collect science, but it is also to collect samples. And I'm wondering how you balance the two. In the old days, back in Apollo, I was actually in the Mission Control Center, and there was somebody with a stopwatch timing the astronauts at each sample point and saying, now you've done your time, move on. Is there going to be that sort of pressure because you have, in a sense, the future looking over your shoulder?
I can take that one. I'll take that one, Leo. It's a very, very good question. And you're absolutely right. There is some incredible science that we're going to be able to do while we're in situ, the great science. One of the main objectives of this mission is to collect samples, a diverse collection of scientific samples that can be collected by Mars Sample Return. And we do have those tubes with us. We want to make sure that within our prime mission, which is 2 Earth years, 1 Mars year, that we do collect a scientifically justifiable sample that allows us to return to Mars and collect those. So we will be doing science along the way. We'll also be using our science instruments to help us best identify the samples that we do want to collect and bring back to make sure that we are collecting a scientifically diverse set of samples. So I wouldn't say that the stopwatch is going to be on, but we are actually keeping an eye on that we're making progress and covering the ground, collecting as many samples as we can in diverse spots within Jezero Crater.
Thank you, Lori, and thank you, Leo, for calling in. Our next caller is Peter Warren with the Star Tribune. Good afternoon, Peter.
Hi, thanks for doing this. This question's for Silvestri and sort of more about the process and working with people than the actual science. What was it like collaborating with Roger Wiens on the SuperCam?
Well, thanks so much. I'm not sure I got all the questions. I'm sorry for that. Could you repeat the last part of your question?
Yeah, what was it like collaborating with Roger on the SuperCam?
Oh, that's an easy one. It was great. This kind of project between two countries that are so complex, you need to have an excellent relationship between the people first. So with Roger Wiens, we've been collaborating together for the last 20 years, I guess. First on ChemCam, now on SuperCam, and we have future project, hopefully. So it's fairly easy. The trick was for us to have an instrument that could define on different parts. We took in France the upper part on the mast. with simple interfaces with the rover and just one link to the body unit. And they take care, and Roger takes care of talking to the rover. So you define your interface of your hardware, you have a good relationship, and life is easy, honestly, very easy. Good project.
Well, thank you so much for that, Sylvester, and thank you to Peter for calling in. Now we're going to switch over to social media. Remember, you can ask questions on our social media platform by using the hashtag #CountdownToMars. The first question is Carol on Facebook. She asks, does any of the science in the Mars 2020 mission give insight to benefit human health? Luther, would you like to take that?
Oh, I've never been asked that question before. I think that a lot of what we do does help benefit human health in that we're trying to make portable and miniaturize different instruments and different techniques, which you can easily move out into the commercial field. I know that a lot of what we're doing on Mars and what we did for Sherlock is going to be integrated into food chains to understand whether there's contamination, whether there's insects contamination and things like that. And that really does it plays a part. It's commercialization. The laser that we developed will get smaller and more robust and be able to fit in food trucks and things like that. And I think every instrument probably can tell that same story.
Thank you, Luther. Conrad on Facebook asks, when can we see the first video and pictures from landing? Do you want to take that, Jim?
Sure. So everything goes according to plan on Thursday. It's possible we could get the hazard avoidance cameras, HazCam, wide-angle images down in that very first downlink. Of course, we don't know exactly how everything's going to go, but if not then there's I believe Mars Odyssey pass just a few hours after landing, maybe 3 hours or so. That could provide an opportunity for some of the first images. And we land with the mast down, tucked onto the deck for safety, and so we won't pop that mast up for a day or two. And then once we do that, then the Mastcam Zs, the navigation cameras, SuperCam can really start to see the surroundings and the landscape. So I would expect, and certainly am planning, that sort of over the course of the weekend, as various press conferences and other events go on with updates on the mission, that the imaging data will start to roll out pretty quickly. Also, as part of those early downlinks, some of the movies that the cameras are taking as the rover comes down, there are video cameras that are recording the parachute from the rover looking up, that are recording the rover from the descent stage looking down, that are recording the ground getting closer as we get closer to the surface. Parts of those movies could start coming down within the first few days as well. And then looking a little bit into the future as we get preparing for the helicopter operations, we'll be using the Mastcam Z cameras to take movies of the helicopter flights. And I'm really excited about doing that and sharing those movies with the public, as well as, of course, with the engineering team.
We are all getting excited to see that for sure. Thank you, Jim. We have a follow-up question from Leo Enright with Irish Television. Good afternoon, Leo.
Yeah, thanks again. Actually, for Jim Bell, you just mentioned the helicopter. How quickly is this going to happen? What they call their right moment? Is that going to happen very quickly?
I think it's going to happen early in the mission. It's going to take many days, perhaps several weeks, for the engineers to do all the checkouts that are required of the basic rover systems themselves, as well as the scientific instruments. All that has to happen first, a sort of initial checkout phase of the mission. And the helicopter folks are also doing some checkouts of the helicopter and its battery and its systems while it's still attached to the rover. And then, as you may have seen in the previous press briefing, it's a multi-day process, multi-sol process on Mars to release the helicopter, release its protective shield, and then deploy it onto the surface, and then the rover backs away, and there's a bunch of checkouts that happen there. So I would anticipate it could be, many weeks to perhaps even a month into the mission before we get to those first flights. But it's all going to depend on the reality on the ground and how everything is checking out during those initial days.
Thank you, Jim. And now we're going back to social media. Spiffy Billy on Instagram asks, what is the first science experiment to be conducted after landing? Ken, will you take that one?
Sure. Well, as you've heard a number of times now, the first weeks of the mission are about checking out all the systems, the engineering systems that are required to make the rover run, and the engineering aspects of the science systems. So the instruments are being tested. As we test the instruments out, just to make sure that they're functioning correctly, we will, of course, have an opportunity. For instance, the first time we test out the SuperCam laser, we will be interested to hit a specific target, and we'll start to get some science data in. But you asked the first science experiment, and to me, it's the first images that come down. I mean, as soon as we get data, image data really from the surface, we can start making scientific interpretations. So not only is it this sort of incredibly inspiring moment, to me anyway, when we see the first images from another body in the solar system or another place, on a planet we've visited before. It's just such a thrilling thing. But there's also science to be gained from that.
Thank you so much for that. And now we're headed back to the phone. Ken Creamer from Space Up Close. Good afternoon, Ken.
Hi, thank you for taking my question, and thank you for doing this. My question is about taking these samples you're going to put in the drill. Can you talk a little bit about how the team is going to work together and which instruments they're going to use to figure out which samples to drill and to cache? And how many samples do you plan to take in the first Mars year? Thanks.
Ken?
Yeah. So another great question. It's similar to the one that Lori took earlier, looking at the balance between, as the previous person said, sort of science and sampling. Of course, the samples, the time we spend collecting the samples and documenting them very specifically is obviously in the interest of science. So those samples are scientific samples. A large part of the science we do while we're not, actively collecting a sample or in the few days leading up to that, is science that we're doing to provide context for those samples. And so I will just say that on this mission, we've known from very early in our development, that we had major challenges in front of us in terms of our operations planning. And this is because we have tried from the very beginning to pack in an enormous amount of capability to do things really well and to do things really quickly, because this opportunity to select scientifically and collect and return samples from Mars is so extraordinary that we want to be able to really make it as rich a mission as possible. And so we've been planning from very early on, strategically, if you like. It was a 4 or 5 year process that led us to select our landing site. That was all part of the planning. And then once we had the landing site, we could use the science team to plan strategically more specifically. And so as we did that, we would often go back to this quote that's attributed to Eisenhower. That's something like, I've always found when going into battle that plans are useless, but planning is indispensable. And so we know that all this planning effort is indispensable. We have to do it. It helps us get better at refining our processes and finding that balance that we mentioned earlier. The time we spend with the stopwatch on collecting the samples and the time we allow ourselves to be driven a little bit more by our curiosity and letting this discovery lead us to the next. We have to do both of those things to make the best of this opportunity. And really it comes down to the time we spend planning and then our ability to flexibly adapt as Mars inevitably throws surprises at us.
Thank you so much, Ken.
You also asked how many samples we're planning to collect, which is a key question. So we have 43 sample tubes on board. So we hope to collect, 40, around 40 samples, but the idea is that 30 samples could be returned. Those return missions, which are, not final yet completely, but that's the capability that NASA is looking at right now, is an ability to return 30 samples.
Thank you so much. Next question is coming from social media. Amal on Twitter asks, how will the microphone help you in exploring Mars? Can you take that, Sylvester?
Oh, yes, I can, because that's an excellent question, because it's the first time we're having microphones on Mars. Has been tried a few times, was never really implemented. So this time we have two. So one of them is mostly technology, is going to record the landing, and that is important. And if it works, after we land, it's going to be used for science, of course. The other one is part of SuperCam. The idea is it's opening a new world. We know there are sounds because we produce sounds, the rover produces sound, laser produce sounds, but there are also winds, different types of winds that create turbulence. That's one point. The second is that we have an atmosphere that propagates the sounds. It does not propagate very fast. Actually, it's slower than Earth. It doesn't matter so much. It's also dimmer. It's very loud. And the high pitch sounds don't propagate very well. But put everything together, yes, we will hear some new sounds. With the atmosphere, we're going to the winds, we're going to learn about the atmosphere turbulence, the convections, and small scale temperature changes. With the laser is going to hit the rocks, and it's like knocking on wood, on whatever concrete you have. By just listening to this zap, we can infer what is the hardness of the rocks. So it's a new place, a new place to hear, and we're really excited with these two microphones.
Thank you, Sylvester. We go back to the phone lines with a follow-up question from Leo Enright with Irish Television. Leo?
Thanks very much, Marina. Sorry for dominating, but since the opportunity is here, I wanted to ask Dr. Maurice about the French Operations Center for Science and Exploration. I think the acronym is FOXY. Can you talk a little bit about how that is going to operate during the time that the rover is on Mars, and what opportunities are there for young Europeans, French obviously, but also Germans and even Irish, to get involved on Mars with FOXY?
Well, thanks for this great question. And Laurie could introduce that. It's an international, it's a NASA mission, but with an international partnership. And to build the instrument, to do the science, but also to operate our instrument. We have an operations center here in Toulouse at CNES, and it is to support SuperCam operation. But when you operate SuperCam, you need resources from the rover. You need to find what Jim is doing with his camera at the same time, because we're sharing the same mast. So operating an instrument is kind of being part of big game, operating the whole rover together. And for that reason, we have an operations center in France for SuperCam every other week. Rest of the time it's in Los Alamos because we also need to rest. But there's an operations center at Jim Place and at JPL. In Europe, we have another one in Spain for the MEDA instrument, in Norway. So everywhere we are operations center. Of course, it is for the team. We are welcoming our students. It's a great way for them to learn how we operate a spacecraft. And it is by operating a spacecraft, an instrument, you can really dive into the science. And that's really the spirit of this mission, that everyone who is doing science should try, if possible, to be part of the ops process, because that's where you define what kind of science you want to do. It can be in Europe, can be everywhere. In the US, it's all together.
Thank you so much, Sylvester. And on that line of inspiring the next generation, Christina on Facebook asks, how will you be inspiring school children, and in particular girls, into science through perseverance? Laurie, can you take that?
Sure. I think that NASA takes that responsibility incredibly seriously. That we know that the work that we're doing is absolutely inspirational, and certainly, the Perseverance rover is no exception, and Ingenuity helicopter as well, no exception. These are absolutely inspirational, and so I certainly encourage anyone that's out there to make sure you check out. We've got materials that are available online at go.nasa.gov/Mars Toolkit, I believe. And make sure you check that out because STEM Toolkit. I think it's the Mars STEM Toolkit. And make sure you check that out. There's all kinds of ways for students around the world to get engaged through the Mars Perseverance Challenge. Get engaged there. There's lots and lots of opportunities for engagement and to get involved with NASA and come along with us as we go through this incredibly exciting time to land, but also as we go forward. Stay engaged and follow us as we explore Mars.
Thank you, Lori. And another question for you from Citizen Science. Are you going to accept volunteers to analyze information we get from the rover?
I can take that one as well. There are always opportunities for citizen science, and this is another area that we are really excited about, the incredible discoveries that citizen scientists are making across the board in so many different disciplines. And of course, we're going to have tons of data available through this mission, and I'm sure that there will be opportunities. I don't know of them specifically that I can cite right now, but I know that there will be specific opportunities, and I don't know if any of the instrument folks that are online with us know of anything related to their instruments they might want to share, but I know that there's going to be an incredible amount of data, and citizen science is a great opportunity, again, to enhance what we are able to do with our science teams, which are only so many people, and there's just an incredible amount of data out there.
A lot of ways to get involved.
Yeah, I could chime in a little bit on that as well. Marina?
Go ahead, Jim.
Oh, sure. So just a couple of things from the imaging perspective. We will be sharing all of the images from all of those cameras on the rover shortly after landing. They'll go out onto a website that JPL is hosting, and we've done this with previous rovers, Spirit and Opportunity, and other NASA missions. So that gets real data, imaging data, into the hands of anybody who wants to do anything with it, and sort of acknowledging the fact that there is a large community of amateur imaging enthusiasts and people who make their own Andy Warhol false color composites and mosaics and panoramas. Will have a place on the ASU Mastcam-Z website where people can upload the products that they've produced from Mastcam-Z data. And then we'll feature some of those and talk about what kids are doing or kids with their teachers for class projects or just other enthusiasts. So I totally agree with Lori that our aim is to involve as many people as possible, getting their hands on some real data and making some real contributions to this mission.
Yes, Ken?
Yeah, I just wanted to quickly say we are looking at some very specific citizen science initiatives that aren't ready right yet, but do stay tuned and join in with us down the line. But I also wanted to comment on the last question: what are we doing to inspire young folks? And I was just thinking about it as we were talking, and the earliest. So we're collecting samples with the intention that they could be returned to Earth for future work by maybe scientists who are currently working or future scientists. And so imagining people on a trajectory where they go, say, straight from an undergraduate science degree straight into graduate school and have a graduate school, a PhD project that's working on these samples. The earliest they will come back is 2031. So if a student is, say, 22, graduating from college, getting ready to go to grad school, that person could be 12 years old right now, 10 or 12 years old, out there just getting, really turned on to science. So I think Mars Sample Return, in that it's this intergenerational effort, is just a great way for, science teachers and us as a world community to get and stay excited about science. The potential is so enormous.
Thank you so much, Ken. Yes, that potential is there. We unfortunately can't answer all of the media questions on air. For those of you with additional questions, please call JPL's Digital News and Media Office. We'll also continue to answer your social media questions online for the rest of the day. Thank you for your questions, and thank you so much to all of our panelists for joining us today. Tomorrow at 10 a.m. Pacific Standard Time, we will have a briefing giving us a final landing mission update, and then at 12 p.m. we'll dive into a briefing on searching for signs of ancient life and the Mars sample return mission. Perseverance is set to land on Mars on February 18th with commentary beginning at 11:15 a.m. Pacific Standard Time. And we are offering lots of ways to ride along with us. To join the virtual NASA social and virtual guest events, register for the Mission to Mars Student Challenge. Lori mentioned this earlier, and live stream the Mars landing. Visit go.nasa.gov/Mars 2020 Toolkit. For those of you interested in a deeper dive, we have a new press kit available online too, with lots of information and graphics describing the rover and its mission. There you'll also have a chance to sign up to send your name to Mars on NASA's next flight to the Red Planet and put yourself right into the action with our Perseverance photo booth. You can pose next to the rover, place yourself in our mission control, and even see what you might look like taking a selfie on the Red Planet. Again, it's all available at go.nasa.gov/Mars 2020 Toolkit. If you're on social media, join the conversation with the mission on Facebook and Twitter. Follow at NASA Persevere and use the hashtag Countdown to Mars. Thank you so much for watching with us today, and go Perseverance.